I'm going to plot the damping ratio for you, so you can see what changing the variables are going to be. Well, how is it going to affect the damping ratio? So we have three main variables that define the damping ratio, which are the specific span, the center of gravity, non-dimensional, and the non-dimensional length of the nose. So I've plotted it. This is a plot for. By the way, I fixed the density. So I took air density 1 and the rocket density 650. That could change a little bit. Again, it's inside square root. Yeah, it can change a bit. But as you see here, I plotted out the rest of the function. Chose x for the specific span, y for the specific center of gravity, and in this plot I chose the specific length of the nose cone, 0.4. So I chose it to plot it from specific span from 2 to 5 and center of gravity from 0.5 to 0.75. As you can see here, max value is 0.12 and it goes down up to 0.5, so it's really bounded in what I told you before. So and if we change the length of the nose cone as, for example, 0.1, which would be a relatively small nose cone, 0.4 is a large nose cone, 0.1 is a small nose cone. As you'll see, the things won't change too much. Let's see if it plots. Oh, great. Alright. Looks a bit different, but maximum value 0.12, 0.7, 0.6. We're at the same situation, and it won't make much change between 0.6 and 0.12. In terms of resonance, it's gonna be catastrophic if we have resonance. For a faster response, remember the response, the inverse time constant was damping ratio times the natural frequency. Yep, indeed. It's still double the damping ratio from here to here. So this is a high center of gravity and high span. We'll dampen out. Well, we can't just conclude that just yet because we still have the angular frequency, the natural frequency we haven't looked into. But for the same natural frequency, high span and center of gravity moved up to the nose cone would dampen out a perturbation faster.